We have been discussing about some of the basic concepts related to surface tension and surface energy, and we have just realized that several things. Firstly, we have learned the Young's equation, which is valid when you dispense a drop of liquid on a solid surface and it makes a finite equilibrium contact angle. We also realized how to discriminate between the different wetting regimes on a flat surface, and they are complete wetting, and I am deliberately going a bit slowly because this is a new course for many of you, where theta e is essentially 0. You actually get a film, liquid film fully covering the solid surface, and the second possible regime is the partial wetting, where theoretically or in principle theta e varies between experimentally people have shown values close to 165 degree with water. And here if the liquid is water, depending on whether theta e is less than 90 degree or theta e is more than 90 degree, you term a surface to be hydrophilic or hydrophobic. From the Young's equation, by doing a simple balance, you can in fact convince yourself that hydrophobic surfaces or surfaces on which the equilibrium contact angle is higher actually has lower values of gamma s, lower surface energy, and on the other hand surfaces on which water or any liquid spreads has higher surface energy. As I have already told, water has a pretty high surface energy, that is 72.8 millijoule per meter square. So, there are it is possible to make various surfaces, particularly surfaces coated with Teflon, which is known to be one of the lowest surface energy material in which water exhibits significantly high contact angle. But an interesting thing is that most of the organic liquids or solvents like alkanes, they have very low surface energy. Their surface energy itself is in the range of 25 to 30 millijoule per meter square, and therefore they tend to spread almost over anything, any surface. So, for example, one perennial problem of this particular phenomena you have is that all your touch screen devices like your smartphone or whatever, you will invariably see that after using it for few days you have marks of fingerprint on them. What happens is that fingerprint actually contains oleic acid. Oleic acid is a pretty low surface energy material, and therefore it leaves it spreads on almost any surface, and dislodging it is rather difficult. Anyway, we will look into certain additional aspects, but before we move on, so one of the things is as we have discussed in the introductory classes, that hydrophobic surfaces are pretty important, or artificially creating hydrophobic surfaces actually makes a lot of sense, because you might want to have self cleaning surfaces, or you would like to, let us say because of rain water drop accumulates on a surface and you would definitely like to remove the water so that the surface becomes dry and fresh, and all that essentially requires that water should not spread on this surface. So, one of the essential or necessary conditions of this so called self cleaning surface is to have a hydrophobic surface. Before we move on to with the concepts of hydrophobicity further, I would also like to introduce the concept of what is known as spreading coefficient. It is a very simple concept, but a very powerful concept, considering a very basic concept or fundamental concept of thermodynamics, that any process, any natural process leads to minimization of free energy. So, what is spreading coefficient? You just remember, you do not have to sort of remember anything by heart. It is represented as SSL, as a solid liquid spreading coefficient. All you need to remember is this particular picture. Suppose you had a pristine surface which had a surface which has surface energy gamma s, and then you take a liquid or put a liquid on it in a manner as if the liquid forms a film. Do not worry about what is the equilibrium contact angle when you are talking about the spreading coefficient or defining the spreading coefficient. Of course, all the considerations are valid. So, if the liquid spreads fully on the solid surface, so this is going to be the configuration. So, you just need to subtract the energy per unit area, the initial configuration minus the, let me put it as surface energy, total surface energy, or the total energy ascribed at the surface in the final configuration, and that gives you this expression. So, just remember this picture and the expression automatically forms. What is the utility? Suppose you have SSL to be negative. What does it mean? It means that after creating the film, it numerically means that the summation of this term and this term exceeds this. So, what does it mean? That after creating the film, there are techniques, trust me, we will learn, and one of them is spin coating. Let me also tell, where it is possible in fact to overcome the equilibrium contact angle by applying excess amount of external force, and can force a liquid to spread on a non-wettable surface. It is there. So, irrespective of whatever is the value of your theta e, you can theoretically or even in experiments, in practically also, you can get to this configuration. But even if you create a film like that, what a negative value of spreading coefficient gives is that by creating this film, you have in fact increased the total amount of energy ascribed at the surface, and therefore, it is very likely that you have gone in the opposite direction of a natural process, and you have created a film that is thermodynamically unstable. You can still do maneuvers and maintain the stability of the film over a period of time. So, you can do some kinetic stabilization, or you can do some other clever things to make a film stable, but the thermodynamically this type of a film is unstable. In contrast, if you now have a situation where your SL is positive, what does it mean? It means that by creating the film, you have in fact reduced the total energy that is ascribed at the interface, and therefore, it is thermodynamically favored, and the film is going to be unconditionally stable. I do not know how many of you have seen a silicon wafer. That is something that is the heart of microelectronics, and the photolithography we talked about, the photolithographic patterning will be performed on a silicon wafer, we will discuss. Silicon as a material has very high surface energy. Its gamma s is of the order of 428 millijoule per meter square. This is extremely high surface energy. So, see, when you are talking about spreading coefficient, surface energy is very high. So, what happens is, the moment you bring out silicon to atmosphere, it actually undergoes some surface oxidation. The oxygen present in air immediately attacks this bare silicon and forms a very thin oxide layer. which has a thickness and it can be measured of the order of 1.5 to 1.8 nanometer. This is called, often called, the native oxide layer. And what is the consequence? Why does this layer form? In fact, if you now take a silicon wafer from in your laboratory and try to measure its surface energy, you will always get gamma s is of the order of 55 to 60 millijoule per meter square. So, there we go. By way of forming this oxide layer, there is a significant reduction in the total surface energy, or the spreading coefficient in this particular case for this oxide layer is very, very high. And trust me, removing this particular layer from silicon, which is necessary for doping, is very, very difficult. So, this is the concept of spreading coefficient. Now, what we would be interested to look into is certain aspects of hydrophobicity in somewhat detail. Primarily for various types of engineering applications, and taking a clue from the natural world, particularly the lotus leaf. So, from the Young's equation, we already know that one of the ways increasing theta e is reduce gamma s. However, please be informed that Teflon, chlorofluorocarbon, that is sort of the lowest surface energy that is available till date, and its surface energy is of the order of 10 millijoule per meter square. So, it turns out of the order of 10 millijoule per meter square. It turns out that if you plug in a value of 10, you cannot really go often to values more than, let us say, of theta e is somewhat in the order of 120 degree, not more than that. So, what does one do? One takes the clue, as I already told, let us say from the lotus leaf, where you can just search the microstructure of lotus leaf in Google, and you can see that there are some micron scale structures. Unfortunately, I do not have an image. The next lecture or some lecture I will show it definitely present on the lotus leaf, and it turns out that it is also covered with a wax like material. It is obvious that this wax like material is responsible for the low energy part of the surface energy, low energy coating, but there are this additional presence of these structures which also contribute to the effective hydrophobicity. And let us find out how the presence of the structures can affect. So, what can happen if you actually have a structured surface? So, what we are considering is we have a structured surface or a patterned surface, and I will just draw it here again to explain to you what can happen. Roughly same pattern, different pattern, whatever. If you now put, so compare this, we are comparing this with the situation of putting a drop of liquid on a solid surface. Now, what we have taken is structured surfaces of the same material. So, these are essentially structured surfaces of the same material over which a liquid, let us say water, was exhibiting an equilibrium contact angle of theta e. Now, the question to ask is, if you sort of dispense a drop of liquid on these structured surfaces. Question number 1, does theta e remain the same? And question number 2, a bit non-obvious, what is the configuration of the liquid? This is a very obvious question, but maybe to some of you the question number 2 itself is little hazy at this point of time. Let us see what I mean. Suppose you put a drop and it is only obvious that this drop will flood the areas between the patterns, right, and that is exactly what is shown here. And in fact, you can still identify some sort of an equilibrium contact angle equivalence which is not equal to theta e for sure, but there are certain expressions which we can calculate, we will do that. But let us look into the other possibility before we write down the expression. The other possibility is more exciting, but it happens, and the possibility is under appropriate condition, and you will have some idea about what this so called appropriate condition is. The liquid fails to penetrate into the gap within the patterns, or in other words, there are. So, these are the structures, and what you have here, you actually have air pockets. Again, here you can have a equivalent equilibrium contact angle, but well, these two in the two cases are not same. This is something new that you are probably learning, some of you are learning. This is what is known as Wenzel state of wetting. This is what is known as Cassie or Cassie-Baxter state of wetting. This and this are rather similar in the sense that in both the cases the contact angle is the area under the liquid drop is fully a liquid solid contact area. In this case it was flat. However, in this particular case it is not flat, it is structured, but the liquid conformally adheres to the surface structure. In contrast, here something more exciting takes place. Here the contact area is no longer a solid liquid contact area only, but it is sort of a composite solid liquid air contact area. So, what is the utility or where exactly it will show up? The most logical thing is to assume at this stage is dislodging a liquid on a surface like this is probably going to be easier. This is intuitively what you can say. We will see that, but before that let us take a look what are the values of theta star e we get, and here it is given as this equivalent equilibrium contact angle on a structured surface for a Wenzel state is given as this, where R is the roughness of the surface. This is interesting because apparently we started this discussion with the basic understanding that you make a surface patterned or structured, and immediately your contact angle will increase, or the level of hydrophobicity will increase. But if you see here, if your initial theta e is less than 90 degree, in fact what turns out is theta star e is lower than theta e. That is very interesting. If you now have an hydrophilic material, structure it, and the wetting regime is Wenzel, you in fact end up reducing, or you end up spreading the liquid more on that surface. Therefore, it is very important that you know the initial equilibrium contact angle, only then patterning the surface might help you in increasing the effective or equivalent contact angle. Obviously, you can also see if theta e is greater than 90 degree, theta e star is going to be theta e. Why and how it happens? You just take a value of r that is greater than 1. Of course, a rough surface will have a roughness value of greater than 1, and you simply plug in some number, that is so you multiply this with a factor that is greater than 1. So, if the value is positive, you are in the first quadrant, and therefore, your theta e reduces, theta e star reduces than theta e. If you are, however, in the second quadrant, you get a negative value, and therefore, theta e star increases as compared to theta e. A bit more complicated relation is given for or one can also write theta star. You can write this as theta star. That is the more common notation. What is given as is another new factor f comes in. I will explain it in a minute. Rf is the same roughness and f is the ratio or it is the fraction, in fact, fraction of solid liquid contact area under the drop. So, 1 minus f in fact refers to the liquid air contact area. So, these areas in the picture contribute to f, and these areas contribute to 1 minus f. Now, how can one do that? In fact, one can show that or I will show it that if you increase the value of roughness, it is possible to go to have a transition from Wenzel state to Cassie state. What are the advantages? I am coming into it, but when does a transition? So, the statement I make is increase the extent of roughness, there is a possibility of heading towards the Cassie state. And is there a critical roughness? Yes, there is. Simply plug in the two or equate these two equations. So, you have a critical roughness theta star or theta c, where the equilibrium angle, the effective contact angles from the two relations are going to be same. So, simply put r cos theta e is going to be r, because r f and r are same, into f cos theta e minus 1 minus f. So, if you do a transposition, what you get and or let me write RF in both the cases. And what are we looking at? We are looking at a sorry, this remains theta e. So, what you get? We are essentially looking at RC, a critical roughness. So, what you get is cos theta e. Please understand that the roughness is not negative. You need to have theta e has to be greater than 90 degree to achieve Cassie state of wetting. What is the advantage? It is obvious that if you now tilt the surface, the adhesion, since there are air pockets, is going to be less, and therefore, the drop is going to get dislodged easily if the wetting state is Cassie. And that is one of the requirements of a super hydrophobic surface or whatever. In the next lecture, I will spend some time on defining what is a super hydrophobic surface, and it is not only the equilibrium contact angle that determines whether a surface is super hydrophobic or not, but there is another parameter which is known as the contact angle hysteresis or CAH, which is also an important parameter that determines whether a surface is super hydrophobic or not, and we will start our discussion from this point. Thank you.